could do, so, you know, the carrier could say, okay, your CPE has this MAC address, so I'm gonna assign you this specific prefix and you're always gonna get it. So that's actually possible. More typically, if you're hosting a web server, probably not gonna be a residential type account, it's probably gonna be a business type account. And then either you would get a fixed one, or more likely you would have more like business class equipment, and they would just configure it so you use these networks.
Well, what about like a NAS or something that it's connected to the network that you would use that way, that you might use across the internet?
I mean, if it can, as long as it can do DHCP, I mean that's what DNS is for. So you do dynamic DNS, and then you look up the name that way, and you should be able to always resolve it like that.
I mean, your 16 networks are still available out on the internet. Like, they gave you 16 networks. Those are publicly addressable networks.
Yeah. Yep.
Right. So it's not like.
So it's assuming pretty much everybody has a firewall. So assuming the firewall allows it, yes. But yeah, they're all publicly addressable. That actually takes some getting used to.
It makes the firewall really very important too, because we've all been using NAT for a firewall, and it's been doing the job.
Yep. I'll come back to that. So sorry, I didn't.
If there's so many IPv6, why are you not getting static IP address, IPv6 networks or addresses?
You could use static. So you definitely can use static. The problem with static is this, right? If we look at where things are going, I mean, the easiest example is light bulbs. I mean, just in this library alone, how many light bulbs do you think I have? Thousands?
Mm-hmm.
So if I look at my network administrators, right now they're managing thousands of devices. In a couple of years, they're going to be managing tens of thousands, and then hundreds of thousands, and then millions of devices. So if I am one person and I have like 500,000 devices to manage, can you see how static addressing could be a challenge? So it's not like you can't do it, but the problem with static addressing is it's just not scalable. There has to be a way to automate things, because where we're going with billions and billions of things on the network.
Because you want plug and play.
Yeah, you have to, because we
After
don't.
imagine that many.
Even if we wanted to do it statically, we don't have the manpower.
Right.
I mean, we don't have enough people. I mean, if you had to configure 1 billion devices, I mean, we don't have enough people to do it.
Full-time job forever.
Yeah. So it's basically forcing more automation.
Oh,
Okay.
Yeah.
Okay.
The address you use internally to access your printer, because you got it on its own network, would be the same address you would use outside from the library to access your printer.
But I mean, if you go back, that came out in I want to say in the mid to late 90s. So if you were in networking before, I mean, we used to use public addresses for IPv4. And I remember when I went to school, I mean, we got all public addresses. When I went to school, private addresses didn't exist yet. So I mean, it's hard for a lot of people, but I mean, if you've done an industry for a long time, and been the whole private address thing.
We've been so long going into our routers and setting, go to the little tab that has the little thing to write, you know, for this port on the router over to this IP address on this other port internally or whatever.
As technology becomes more and more pervasive, though, I think the easiest way to look at it is like this. So we have actually a similar problem with phone numbers, where we're running out of area codes. So, you know, in technology, we just think, you know, we'll do NAT, whatever. But if you talk to somebody outside of IT and say, you know, I'm really sorry, but you know that house you bought in the new neighborhood? We don't have any more phone numbers left. So here's what we're going to do. We're going to give one public phone number for that whole neighborhood, and you're going to be behind a PBX. And then when you know, it's not a big deal. When people want to call you, they just call the number, they put in your and I mean, what's the problem? But you know what? I've actually talked to a lot of non-technical people, and they look at me like I'm crazy or they're going to kill me. They're not taking away my phone number, right? So that's the idea of IPv6 is we need to get back to that. That people can just, you know, you can just call somebody, right? It shouldn't be a big deal.
That's why you do that with phone numbers in companies right now.
Yep.
Every desk
Everybody
has
wants a
an
DID.
external phone number.
Yeah,
Yep.
back in anything.
Okay, so I don't want to spend. This is kind of a reference slide, but just so you know. So if you look at these addresses, if you look carefully, and I'll come back to this, you'll notice that there's a resemblance to the MAC. So this kind of drives me nuts. A lot of people say that we have 64-bit interface identifiers because, I don't know, IEEE wanted to make our life hard or something like that. So again, I didn't actually explicitly put this, but IPv6 is a 128-bit address. So half is the network and half is the interface ID, the network or the prefix. But basically how I get to you, and then the second half is the interface ID. It's always like that. So the idea is, how many people like subnetting in IPv4? Really, you like it?
Well,
Okay, so I can tell you from teaching at college for almost 10 years, what is the single hardest networking concept that causes a lot of people to drop out of networking? Subnetting. It's actually somewhat challenging. So on IPv6, there is no subnetting. Everything's a /64 and that's it. So that's why I don't spend a lot of time talking about it, because it's just gone. So now this is also hard for people to get used to, because IPv4 it's about conservation. So in IPv6, every network has 18 quintillion addresses. And people are like, you can't do that. That's illegal. But I mean, think of it like this. If I look at my parents live in Farmington Hills, they have 5-digit addressing, right? So 5-digit addressing, they could have 100,000 homes on their street, and they only have 5. Isn't that a waste? How can we allow that? But who cares, because addressing is unlimited, right? So I mean, that's what we need to get back to. All right, so the reason we have 64-bit addresses is actually because of FireWire is the best example. So the IEEE has actually had 64-bit Macs for a long time. So if anybody has FireWire on their computer, you'll notice it actually uses a 64-bit Mac. This has been out for a long time. That's the real reason. It's not because, you know, they're trying to make our life hard or anything. It's just to accommodate everything they had. Because the IEEE saw the same thing. 48 bits is not enough. With all the devices that require a physical address, we're going to run out. So they changed to 64. So if you don't have a 64-bit address like Ethernet, then you have to add FFFE in the middle to basically convert it to a 64-bit hardware address. So that's all that is. So that's where this FFFE comes in the middle. Now, there's one more thing. When you take your MAC address and change it into an interface address, you have to flip the unique local bit. And this drives a lot of people nuts, because it's like, man, why do I have to do that? But there's actually a really good reason. So if they didn't do it that way, let's say I want to create a router. And a lot of times when I create a router, if I create a router, I'm going to make the router's address FE80::1, because it's easy, right? But if they didn't flip this bit, I would actually have to make it FE80::0200:00:1, right? Because I'd have to flip the unique local bit, because that's a locally assigned address. So to make our lives easy, so if we want to be able to do something like this, they basically flipped it. So this is assigned globally, right? This is assigned from the IEEE. So the unique bit should basically be 0. But we're flipping it so that if somebody assigns local addresses, it makes it easy. Does that make sense? In the
It's a
lower
shorthand.
left-hand corner?
It's a shorthand way of saying it, right?
Yeah. It basically, if you're creating local addresses, it makes your life much easier. So I mean, I know that's a little confusing, but it was actually done that way to make our life easier. So it's just a reference. Okay, so when I look at from ifconfig, so here's my MAC or my hardware address, and you'll notice that it follows that pattern, right? I flip the unique local a bit. Here's the first half of my MAC address.
Oh,
here's
yeah.
FFFE. Here's the second half. So that's where I'm getting those addresses from. So that mostly works, except for there's 2 things. This address totally doesn't follow that. And I guess the other question that I usually get is, so as soon as I turned on the router for it to advertise the network prefix, all of my hosts have 2 addresses. Why do they have 2?
Public and local?
So if I look at it from the IP command, it'll actually show me a little more detail. One of them is a temporary address. So because everything is, or most things access the internet, anybody see a problem if my address, and remember, my interface ID is always the same. So if my interface ID is always the same no matter where I go, no matter which network I access. Anybody see a problem with that? What did I just create? Self-tracking. Right, I basically, my MAC address is like a super cookie, and they can track me wherever I go. Right, so in IPX, we didn't care because we didn't really have, there wasn't an IPX internet. But with IP, this is actually not a good thing. So, in order to fix that, they said, okay, well, we can't have that because then you can track everybody. So there's a second kind of address where we randomize it. So the whole 64-bit address is a random number. And it's also temporary, which is, this is a whole other can of worms, but just to make it simple, the idea with being temporary is it changes every day. So the idea would be nobody can track you and you're super secure. So, and from a security point of view, that's good. Anybody have long-lived SSH connections? Like anybody SSH to a server and leave it going for more than a day? Yeah, I do that. So what happens, so if I had this temporary address, and by default, all my connections use the temporary address, so I am more secure, what happens in 24 hours when that address rotates? That's right, I get disconnected. Isn't that cool?
Yeah, but it was secure while you were there.
But you're very secure, so anyway.
So,
There's
question.
a whole other topic on that, but that's the idea.
So flip that around now. Something I hear is called mobile IP. So if you have a device that you want to have the same address to, there's something in IPv6 that allows you to do that. And I'm curious how that works, and so more curious really about the problem of. So now you have an ISP that you go through to get your address. You move to another location. It's like I have AT&T for my cell phone. I come to the library, I connect to their local network. How is it that do I have to have a contract with AT&T in order to connect with the library?
Mobile IP is a very, actually it does exist in IPv4 too, it just never really took off. And IPv6 added some nice enhancements which got backported. It's a great technology. The problem is outside of the cellular industry, nobody uses it. And I don't, it's really a shame because it's a very cool technology that it could be used to solve a lot of complex problems, but there's zero, like Microsoft and Apple have zero interest in basically supporting it in their operating system. So it's very cool, but I mean, it's actually fairly complex. It'd be a whole talk just to go into mobile IP, but I don't think it'd be interesting to most people just because unless you're in the cellular space, you'll never see it. Unfortunately, I wish that wasn't true, but sometimes that's how it works. The IEEE or the ITF come up with a really cool technology, and companies, for whatever reason, just decide, like, nope, I'm not going to do it.
Well, the thing is that it will loosen up their tie to you paying them to get access.
No, because they, I don't think that's done by IP. That's done by the PEP context, I think, which is different. But it's
tunneling kind of thing or something like that?
so basically with mobile IP. So I have a home. You know what? The easiest way to think of mobile IP is just like your cell number. So when I roam from tower to tower, does my cell number change? No, it always stays the same. So mobile IP would let you do that. Mobile IP would let you do that with an IP address. So it's very cool because wouldn't it be nice if you could power on your laptop and you could have an SSH session or a VPN connection or something like that, and you basically roam from wireless to Ethernet to 3G to 4G, go all over the place, and it just always works. Wouldn't that be nice? Just like a cell phone, and the technology exists, but Apple and Microsoft, they don't want to do it. So sometimes that's how it goes. So this is my privacy address, and then sorry. All right, and then, so I don't know if this is constant across Linux. I'm not sure, to be honest. In Ubuntu 12.04, the default is 2, which means that privacy is on by default, which means that I use a temporary address. The temporary address is a random number, and it changes every 24 hours. You can also change it to one. One is I have a privacy address, but I actually use the other address for my outgoing connections, which I mean, doesn't really make any sense. Or you can turn it off. I think you'd either use 0 or 2. And actually, you can use, 10 and -1 if you want, but I would stick with 0, 1, and 2. So some people do turn it off. So in I think privacy addresses, I think, are good for consumers. In an enterprise, they're a nightmare. So in an enterprise, I would turn it off, and I would use DHCPV6. Because you don't want everybody to have, a couple different addresses that constantly change. Because then if you try and troubleshoot something, good luck.
When logging is done on the network, is the logging of, like, for outgoing requests, is the logging of the temporary address or the permanent address?
It's, the logging would be of the address you use. So the answer is it depends.
Depends on that used template,
Right,
Yeah.
but I mean, by default, 2's on, and so 2's temporary,
Well,
because
if
that
you want-
temporary
if
goes
you
away
want to-
tomorrow.
Right.
So that's what you're saying
Actually,
about
Jim,
tracking.
I don't think it's the same in all distros. I
No.
think it's different.
Okay.
I don't think so, and also it depends on how old it is,
Yeah.
right? Because, a lot of times you have a server that works great, so you're not gonna upgrade. So I really, I guess one challenge, and this is interesting to me, so, most of what I get paid to do is either Cisco or Microsoft. So conceptually, I know this stuff backwards and forwards, but even when I was writing this presentation, it was kind of interesting because it's like, okay, I know what I wanna do, how do I do that in Ubuntu 12? And that's, with IPv6 you'll find that, you do it this way in this distro, you do it this way in OS 10, you do it this way in XP, you do it this way in 7, you do it this way in Server 2012, you do it this way in Cisco, this way in Juniper, this way in Brocade. Everybody's got their own. So it's not hard, but it's just, at scale it gets, because everybody has their own, twist or their own utilities or their own ideas, so. Okay, one thing I do want to mention, this is another big change that's important to understand, and there are a lot of religious wars with IPv6. This is one of them. So essentially, there's kind of this tension between, there's what I would call more of an enterprise mentality. So people that want control over everything, they want DHCP to control everything, and that's it. Total control. That's more the traditional enterprise. Then there's more of the consumer/educational mentality, which is everything's open, no control, decentralized, plug and play. Right? So you have these totally, and it's interesting when you go to the conferences and you'll hear like the enterprise mentality person and the university mentality person talk about the same thing, and it sounds like it's a different technology. It's just perspective. So when IPv6 came out, there was the one group that was all pro plug and play. They wanted everything to just plug in and work, right? So they want everything to be in router advertisements. They wanted to kill off DHCP. DHCP is bad news. We don't need it. It's too complex. Just get rid of it. Then you had the enterprise people that are like, I only want DHCP. I don't want anything else. And they're still going at it today. And so we kind of got this compromise. So you have to have router advertisements. So like that router advertisement daemon we set up, you have to have that. So on IPv6, you cannot get a default gateway from DHCPv6, at least currently. You have to have that router advertisement daemon. That kind of makes sense because typically I have centralized DHCP, and my local router is going to know best who the gateway is. So I can kind of see that, but it does make it a little more complex. There's a little bit of overlap. So originally, if I want my parameters like DNS servers, for example, are pretty important, I had to have DHCP. Recently, in the last couple of years, they changed it, so now I can get that from router advertisements as well. But by default, most Linux distros don't support it. You have to install a utility. Windows doesn't support it. OS 10, I think they added it in 10.7. So support is pretty limited. But there's very divergent opinions on that. It just depends on what you want. I would say if you run DHCP now, I would stick with DHCP. For home, you probably don't need it. Okay, so in order to make these guys work, right, so remember there's that hook into the router advertisement daemon. So I have to go back into my conf file, and there's two flags. there's essentially the managed flag and the other flag. So the other flag is if the router advertisement daemon, if it's basically doing Slack, where it just hands out a prefix and everybody automatically configures themselves, then I don't need to get an address from DHCP. So then I have the other flag. So the other flag says, okay, I already gave out addressing, I just need DNS or whatever else. You know, maybe for my phone I need a TFTP server, for example. So what that's going to do is it's going to tell the client sees that flag in the router advertisement, the client's going to go out and say, give me my DHCP parameters, like my DNS server. The other flag is the managed flag. If the managed flag is set, that's basically traditional DHCP. Give me my IP address and give me all my parameters. So I can have either or both set. All right, and this is just a simple example. It looks, at least with Ubuntu, they use ISC's DHCP server. It's already built into 12, so you just have to play with it. I kind of ran out of time to actually get it to work with the service command, so I actually cheated and did it from the command line. But the configuration is pretty simple. You just go into the conf file. There's a basic one for your options, pretty straightforward. And this is a range of addresses they hand out. So I mean, obviously there's a bunch more stuff, there's man pages, but I mean, you get the idea. It's relatively straightforward. Now, another thing, remember, with IPv6, I have multiple addresses by default. So, if I have my router advertising prefixes to do Slack, and I turn on DHCP to hand out addressing, which one am I going to use? Both. So I'm going to have three global addresses. Right? It's cumulative. So every method you turn on, you're adding more addresses. So keep that in mind. Yes, sir?
Earlier you were talking about groups, IPv6 groups.
Multicast groups, yeah.
Yeah, would the DHCP or would it be router advertisements that configures that? Or is that statically configured?
So there's a lot of components. So at the simplest level, multicast just works on one network, right? So if I have a simple multicast setup, it's just on that network. So what happens is, when I send out a multicast, you essentially, the node has to be configured to listen for that multicast group. So, for example, with the solicited node multicast address, when I configure an IPv6 address and I join that solicited node group, then basically I'm programming my network adapter to say, hey, any packets that are sent to this group, I want them.
Okay.
And so the nodes are basically joining those groups. So when somebody transmits a packet to that group, you basically program, whether it's wireless, wired, cellular, you programmed your adapter to say, I want that traffic. Because by default, it's ignored. That's the difference. That's the difference between multicast and broadcast. Multicast, you have to opt in. Broadcast, you get it where you like it or not. Multicast, you have to say, I actually want to receive this. So that's, at a local level, you're basically joining the group and then you're receiving that traffic. Now, if you go past the local network where you route it, then it gets a lot more complex. And that would, to be honest, that'd really be a whole talk of its own.
Sure.
Did that answer your question?
Yeah, it's statically set.
Yeah,
the
pretty
machine.
much. There are, in dynamic registration, where, like, let's say I want to create, let's say I install a video server, and I want that video server to automatically register a multicast address somewhere, and then have my clients automatically join it. I believe that's an area of work. So I think some vendors have a solution. I don't think there's a standard way to do that yet. But I mean, I think it's using dynamic DNS. So I can use DHCP, I can request a multicast group, I can then register it with dynamic DNS. My clients know to go and look for that particular name and they can join. So that's kind of where we're going. Again, so it's all automatic, but it's not quite there yet.
Okay.
Any other questions? How are we doing on time?
7 minutes.
Yeah.
All right. So, just tell me when I'm cut off. All right, we're almost through the most part, and then the last section is more reference. So, remember I made that point of showing that when I do ARP, ARP is below IP, but when I do neighbor discovery protocol, it uses IP. This is huge. So, unfortunately, a lot of people have gotten in the bad habit, and this is a bad habit because there's kind of a mistaken belief that all ICMP traffic is bad and I should block all of it. That's a mistake. It actually breaks a lot of things and causes problems. You can get away with it in IPv4, however, if you do that in IPv6, what's going to happen to your neighbor resolution?
Bye-bye.
That's right. So it's going to work until your cache expires and then all traffic will stop. So that would be bad. So this is a big thing for people doing security. You cannot block all ICMP. I mean, you will break your network. It won't work. So actually, there's two good references. Most people don't actually read RFCs, so I threw that at the bottom. But NIST, which is a fantastic part of our federal government, and they actually do absolutely fabulous work, and it's free, right? That's what our taxes pay for, and their documents are fantastic. This is a great document by itself, but you could just go to this one chart, and this is a bridge, it's just part of it, but this chart basically shows you, here are all the ICMP types, and here's what you have to allow, and here's what's gray. And it's basically somebody's done all the homework for you. And if you go and search, you can even find people on the internet that have basically followed Special Publication 800-119, and they'll say, here's a set of IP table rules to implement that. But that's where you want to start. Question?
You said before that the MTU, if packet needs to be broken down in fragments, that has to be done on the end node, it can't be done by a router.
Yep, correct.
Is that why there's an item up there that ICMP packet too big has to be transferred back and forth so that the host knows not to use it?
Actually, just made me very happy, because the last slide I put together today was a slide to answer that question. So I will answer that question in a minute. So the reason that fragmentation was eliminated is because fragmentation causes severe performance degradation. So if I have you know, on a small scale it doesn't matter, but if I have a big data center like Facebook or a sizable company, and there's an MTU mismatch where I have to fragment traffic, that kills my network equipment. It kills it. So the performance tanks. And so a decision was made, and it's not one particular vendor, it's all vendors have that problem. So a decision was made, that's it, no fragmentation. The host has to do it. You push it back to the host. If it's distributed, right, fragmentation is a performance issue. It goes back to the relay. If we're doing it all centrally, it's a scaling problem and we can't do it. But if we push it out to the edges, most computers have plenty of processing power, then it's not an issue. So that's why they did that. Push it out to the edge, the problem goes away. But this is the problem to answer your question. So, right now, and at least for the next 5 years, we're going to be, probably longer, we're going to be in a transition period, right? Where we're transitioning from IPv4 to IPv6. That means that a lot of people are going to be running tunnels or translation or proxies or other things like that. But tunnels especially, if I do tunneling, it changes my MTU. It changes my payload size. So here's what happens is client sends a request, right? I try and get to this server. So I didn't show this, but the default MTU for Ethernet is 1500. So typically I have an MTU of 1500. I get to this router. The link between the router and the web server is only 1420. It's smaller. So this router is going to send back an ICMP error message saying, hey, the packet is too big. You have to fragment it so it's at most 1420, right? If that message made it back to the router, the client would automatically adjust, everything would be fine. That's called path MTU discovery. It's not by default. However, a common problem is a lot of people just block all ICMP, period. All ICMP is bad and is dropped. So that message gets dropped, never makes it back to the client. So basically it causes a black hole. The client can't talk to the server. This is actually a common problem. And I put it in the slide deck because this is a really difficult problem to troubleshoot. So I'll give you an example. I was using WebEx, and I have a tunnel at home because my Comcast business class connection doesn't have native IPv6 yet. It's coming this year. So that tunnel lowers my MTU. So when I tried to go to WebEx, I ran into a problem like this. And you know what? I couldn't figure it out. Like, if I could look at packet traces and do testing, and I just guessed, I'm like, it's gotta be an MTU issue. So I lowered my MTU by 40, and then it worked. So these are really different, because the problem is, I don't have access to the middle of the internet, right? Or the customer's data center. I can't see what the far end MTU is. So there are some tools that can help with this, but MTU issues are pretty tough. So you'll see, like in conferences and stuff, a lot of times they'll just set everybody's MTU to 1280, that's the minimum. So that way the issue goes away.